To calculate the current at forward bias, we have to look at the carrier statistics again. Under forward bias, the water level on the P side is lowered, and the barrier height becomes smaller. A large number of electrons on the N side will have sufficient energy to overcome the barrier to reach the P side. It will first raise the electron concentration in the P side neutral region close to the depletion region. These electrons will then diffuse to the other part of the P side neutral region by diffusion due to the carrier concentration gradient. The carrier concentration distribution at forward bias in the neutral regions will be like what is shown in this figure. To calculate the forward bias current, we follow the same approach as in the reverse bias case to find a location to count the carrier flow. And we will pick the same locations as that in the reverse bias condition for convenience. That is, we will count electrons at the P side neutral region edge and holes at the N side neutral region edge close to the depletion region. And the current in these regions also consists of diffusion current, which is caused by the concentration gradient. This also means that the current is proportional to the slope in the given figure. Let's label the minority carrier concentrations near the edges of the depletion regions as NPD and PND accordingly. And both of them are dependent on the applied voltage. It turns out that the length in the neutral region when the slope of the carrier concentration intersects the equilibrium carrier concentration are also the diffusion lengths Ln and Lp, as we learned before. So we can write down the electron current density as QDN times NPD minus NP0 over Ln, and whole current to be QDP PND minus PN0 over Lp. If we assume the depletion region is very small again, NPD is just given by the electron concentration on the N side with energy higher than ECP. As the increase is due to the shift in Fermi level, it can be calculated in the same way as the reverse bias case. That is, starting from the thermal equilibrium condition with carrier concentration NP0 above ECP0, we shift the Fermi level up with VA. The new carrier concentration above the new ECP becomes NPD equal to NP0 times exponential QVA over KT. Then, the diffusion current is just as it is given here. After expanding NPD, it becomes what is shown here. We then collect the common terms and obtain the expression for electron diffusion current in the conduction band. After combining both electron and hole currents, the final expression becomes what is shown here. It is exactly the same as the expression in the case of reverse bias diode current, but here with VA taking up a positive value. It is not surprising, as both currents are controlled by the carrier concentration at the edge of the depletion region as a result of the shifting of Fermi level due to external voltage. We also notice that the terms before the exponential term are independent of the external voltage and become fixed once the doping concentration is known. We often denote it by I0, and we obtain the widely used diode equations shown here. By examining the expressions of I0, you should notice that it is composed of two different current components, one for electron in the conduction band and one for holes. We will spend more time to study the behavior of this equation in the next section.